Hello everyone, welcome back. In this video, we're going to talk about different types of hypothesis testing in statistics. And so you may be familiar with the idea of a hypothesis from the scientific method. You make a bunch of observations, and then you come up with an idea or a concept that explains what you observed. Well, it's kind of similar to what we're going to be doing here. However, in statistics, our hypotheses will be about making a claim or an assumption about an entire population. And then what we're going to do is collect some samples from that population, measure them, do some analysis, and then test our claims of our hypothesis using that sample that we collected. And so the claims we'll be making about the entire population are going to be related to things like the average or mean for that population, the standard deviation, or maybe the proportion. And depending on what kind of claim we're making, it'll kind of dictate a different type of hypothesis test that we may use. But no matter which hypothesis test we end up using, they all kind of follow the same overall structure. And a good way to remember the structure for hypothesis testing is with what we call the 5 C's. So notice each one of these 5 little bullet points starts with the letter C. That's what we mean by the 5 C's. The first step in the 5 C's is we create our hypotheses. After that, we check our conditions, make sure that our test is going to be doable and it applies to the situation. After that, we calculate what we call our test statistic. We then use that in step 4 to compare, and then depending on what happens in our comparison, we will make a conclusion about our original hypotheses. So let's go ahead and break down these 5 steps into a bit more detail, starting with the first one. What does it mean to create a hypothesis or hypotheses for statistics? We're not going to go super deep into the theory of hypothesis testing, but there is an important format that we always use when we are doing hypothesis testing in statistics. It's just kind of part of the machine of hypothesis testing. So in stats, we actually always make 2 hypotheses at the same time or concurrently. The first one we might call the null hypothesis, which is denoted with H with a subscript of 0. And the other hypothesis that is part of our hypothesis test is what we call the alternative hypothesis, denoted with H sub A. So even though we wrote down the null hypothesis first in our little list here, we usually actually start with the alternative hypothesis because that is the claim that we are actually trying to test about our population. So the alternative hypothesis is really the claim we are trying to test, and the null hypothesis is just the assumption that we are making about the population. So we'll be doing an example here very soon to kind of clarify what we mean about these statements of what we test about the population and what we assume about the population. But a couple more notes about the alternative hypothesis and the null hypothesis before we look at an example are that when we're constructing the alternative hypothesis, we never use an equality sign. We're always trying to say something is bigger than something else, less than something else, or just not equal to something else. And these things we're talking about are usually like the mean, the standard deviation, or the proportion, or other things we measure. So our alternative hypothesis will always include non-equality. So we'll say like the average is greater than some number, or we're claiming or trying to test if the average is less than some number, or just not equal to some number. So it could be greater than or less than. And so how does that connect back to the null hypothesis? The null hypothesis is always the assumption we make, and that's going to be the exact opposite of the claim we are making in the alternative hypothesis. And so that's yet another reason why it's actually, I think, better to start with the alternative hypothesis. Once you write down your little claim using greater than, less than, or not equal to, then just looking at the opposite of that claim is how we can construct the null hypothesis every single time. One last note about the alternative hypothesis here is in this video, we're denoting it with H sub A, and that's pretty common, but you might also see it denoted with like H sub 1 instead. But I think we'll always see the null hypothesis with H sub 0 or H naught. All right, so before we talk about the 4 other C's, let's look at a quick example of how we can construct our alternative and null hypotheses. In this example, we're going to suppose that a claim is made that the average mortgage interest rate in the United States is 4.5%. So there are going to be 3 different hypotheses that we could create depending on what we believe about this claim. So the 3 different hypotheses that we could create about this claim are 1, the average mortgage interest rate could actually be less than 4.5%, right? It's claimed to be equal to 4.5%. Or we could check the hypothesis that the average mortgage interest rate is actually greater than 4.5%. And the third situation is the average mortgage interest rate is just not equal to 4.5%. So it could be bigger or less than 4.5%. None of these include equality, and these are all how we formulate the different types of alternative hypotheses. So let's actually write down these 3 different hypothesis tests that we could set up depending on what we want to test or what we think is actually true. And we're going to start with that alternative hypothesis for each one. So in this first little situation, how are we going to formulate our alternative hypothesis? Well, a claim is being made about the average or the mean interest rate. And so we're going to use mu because that's what we use to denote our mean or average for our population. Let's see. And so what we're really trying to test here in this first scenario is our average actually less than 4.5%? And so once we have written down what our alternative hypothesis is, it's really easy to create the null hypothesis. It's just the opposite of what we claim down here. And so what's the opposite of being less than 4.5%? Well, the average could be greater than or equal to 4.5% instead, right? This covers all the different types of situations. And the null hypothesis is always the opposite or kind of the complement of the alternative hypothesis. Okay, let's go ahead and look at our second situation here. Like maybe we actually believe the mortgage interest rates are greater than 4.5%. Well, we could kind of write that claim in the spot for the alternative hypothesis here. And so we're still talking about an average, so that's mu. But now we want to test and see, is the average actually bigger than 4.5%? So our alternative hypothesis is mu is greater than 4.5%. And our null hypothesis is just going to be the opposite of that, or the complement. And so if you're not greater than 4.5%, then you must be less than or equal to 4.5%. Let's finish this off by looking at the third one. The third hypothesis test we could set up here is testing to see, is the average mortgage interest rate just not equal to 4.5%? Well, in that case, our alternative hypothesis will be written as mu is not equal to 4.5%. And that would mean the null hypothesis is that mu, the average interest rate, would actually be equal to 4.5%. And so again, for some emphasis, notice how all of our alternative hypotheses never include an equal sign. That's always going to be the case. And also notice that all of our null hypotheses do include an equal sign or an equality as part of their statement. And as we know, or as we're learning, mathematicians are some of the laziest folks out there. So what we do is for the null hypothesis, you'll often see instead of like the actual opposite of the alternative hypothesis, we just write them all with equal signs, really just out of laziness, but they really should always be the opposite of the alternative hypothesis. So let's just make a little note about that so we don't forget. The null hypothesis is always written with equality, or not always, but it's very common to see it written with equality, and that's what we're going to see in our textbooks. But just know it really is supposed to be the opposite of the alternative hypothesis. And so you might see an alternative hypothesis say mu is less than 4.5%, with the null hypothesis being written as mu is equal to 4.5%. Or if you see an alternative hypothesis that mu is greater than 4.5%, well then our null hypothesis will still just be mu is equal to 4.5%. And for that third case, it's not necessary because it's already written with just an equality. I think that's more kind of annoying and a nuisance, but we just have to remember how to interpret that. It's not actually saying what the symbols usually say. A couple other bits of terminology that we want to write down now that'll make more sense later when we look at some graphs is alternative hypothesis, where we say mu is less than some number, or it doesn't have to be mu, it could be our standard deviation or proportion or whatever we're testing here. Whenever that is less than some number, we refer to that as a left-tailed test. And that'll tie back into probability distributions at some point. Similarly though, if we're looking at a hypothesis testing where alternative hypothesis says our quantity is greater than some number, then that is going to be referred to as a right-tailed test or right-tailed. And when we have the inequality sign in our alternative hypothesis, that's kind of both a left-tailed and a right-tailed test, so we call that a two-tailed test. Or is two-tailed. So creating our alternative and the null hypothesis is just step one in our hypothesis testing process or machine. We've talked about that. Now we're ready to move on to step 2, which is where we check conditions, make sure that we can actually do the things we want to be doing. All right, so let's go ahead and talk about that second part of the 5 C's, checking our conditions, making sure that our hypothesis test is actually going to do the things we want it to do. And each different type of hypothesis test that we'll be doing is going to have a different set of conditions, but all these conditions are trying to accomplish the same thing, and that is that the sample we are eventually going to be taking of the entire population to do our analysis, these conditions are just making sure that that sample is a good representation of the entire population. There are a lot more than just 2 different types of hypothesis testing, but I think in our first couple of videos, as we're just learning about these, let's just focus on 2 types. The 2 types of hypothesis testing that I want to focus on early on are testing means or averages, and then also testing proportions. And so when we're doing hypothesis testing for testing means, like trying to see if the average is bigger than 4.5%, less than 4.5%, or just not equal to 4.5%, one condition that we have to make sure is happening when we take our sample is that our sample truly is a random sample. The other thing that we have to make sure is that the population follows a normal distribution, or if it doesn't follow a normal distribution, that our sample size is large enough that it doesn't really matter. And that number, that kind of magic number, is usually just 30. So again, to recap, the 2 conditions we have to check if we are doing a hypothesis test involving means or testing means is we have to make sure the sample we are taking from the population is a random sample, and we have to also verify that our population is normally distributed, or if it's not normally distributed, we need a pretty large sample size of 30 or more. The other type of hypothesis testing that we'll be looking at early on is tests looking at proportions, like is this proportion smaller, greater, or not equal to some number? Well, again, we're going to require that the sample we take in our analysis must be a random sample. Another requirement for testing proportions is that our distribution has to be a binomial distribution, meaning it's like a yes-no thing. There's only 2 types of outcomes, usually referred to as successes or as failures. So testing means require a normal distribution or a large sample size, but for testing proportions, we require a binomial distribution, or in other words, each trial is going to be considered a success or a failure. There is no third option. Also, for testing means, we required a large sample size. We have something similar for when we're testing proportions, and it can be phrased in different ways depending on the resource or textbook that you're working out of. For our textbook, we say it in the following way. And so what we use from our textbook is if we let n represent the sample size we're taking out of the population to do our analysis, p is going to represent the probability of success for an independent trial, and q represents the probability of failure. So it's the complement, that is q is just 1 minus p, the probability of success. Then our requirement is that n times p, the sample size multiplied by the probability of success, has to be greater than 5. And similarly, n times q, the sample size multiplied by the probability of failure, must also be 5. What these conditions are really doing is making sure that in our sample, as we do this analysis, we have enough numbers of successful trials and failure trials in order to do our analysis. So let's go ahead and move on to step 3 of the 5 C's, where we actually calculate our test statistics. All right, so we're ready to talk about calculating our test statistic. And to illustrate this concept, I'm still going to be referring back to that example of looking at the average mortgage interest rate in the United States. So remember, our null hypothesis was basically claiming that that average mortgage interest rate was 4.5%, and maybe our claim is that it's not 4.5%. Maybe we're trying to claim that it's less than 4.5%. And when we took our sample average or sample mean from our sample from the population, maybe our sample calculated the average mortgage interest rate to be 3% for that sample. And so what we're really trying to do in this calculation of the test statistic is we're trying to see what is the probability or chances of our random sample actually having it be this far or this below the mean. But we're not going to do it with the values we get from our claim or from our sample collection. Instead, what we do is we take that data that we have and we standardize it and reformat it. So we're going to be using some statistics tools to reformat or standardize our data. And what this is going to do is essentially remove the context from the situations. The numbers are going to change, but we're always changing kind of the same types of numbers. So that makes it easier to look at because we might have totally different numbers in a totally different situation. But once we reformat or standardize or calculate our test statistics, everything's going to start looking similar, which is going to make our process for comparing and making conclusions a lot more easier and standardized. And the idea is after the standardization, it's going to be a lot easier to calculate using statistical tools or tables what is the actual probability of our sample average being this number. If it's really low, then we might reject our claim, but if it's not too low, then we might, fail to reject our claim. So into the standardization of our data, instead of the average being like 4.5%, the average is always going to be recentered at 0. So after this reformatting process, mu, or the average, always becomes 0. And instead of working with x bar being 3%, we instead convert that to our test statistic. And so we aren't going to always have the same symbol for that test statistic because it's going to depend on a few things, like what kind of hypothesis test are we doing. And so you often see things like t or z being used as our test statistic. And we're not going to be doing any of this reformatting by hand. We're going to have our calculators or computers or tables assist us in this process. And so after this, we can actually calculate the probability of our sample average being some number like 3%. And we're going to call this or refer to this as the p-value. We can tie this p-value back very nicely into the picture we have up here of our standard distribution of our population. The p-value can always correspond to a shaded region of our standard distribution. What that shaded region is going to look like depends on the alternative hypothesis that we set up. To illustrate this, let's go ahead and suppose that our alternative hypothesis was trying to make the claim that mu was less than 4.5%. Then we can calculate our test statistics for our sample average of 3%. The p-value we get would correspond to the shaded region to the left of our x-bar value. So the p-value is just the shaded area to the left of x-bar in this case, and that's like the probability of us getting x-bar if we remember our facts about probability distributions. And if our alternative hypothesis instead said mu was greater than 4.5%, then we'd be shading the region to the right of x-bar instead. And that goes back to what we talked about earlier as like left-tailed tests versus right-tailed tests. This type of setup is a left-tailed test because where that shaded region is ending up. The other situation where mu is greater than 4.5% would be like a right-tailed test. There is that third situation where mu is not equal to the average, like 4.5%, in which case that is a two-tailed test, but the picture is going to look a lot different, and we'll talk about that later. So in our class, I don't think we're going to be doing these standardizations or reformattings by hand, so we'll be using calculators or tables from the textbook instead. So now we're ready to move on to that fourth C in our 5 Cs, the comparison step. So in this comparison step, we're going to use our p-value and our test statistic to figure out if we can reject our null hypothesis or if we cannot reject our null hypothesis. And the way we do this is we compare them to a critical value or to an alpha value. So this alpha value, this probability threshold, is really almost like a tolerance. The larger your alpha value or tolerance is, then it's like the more okay you are with having a random sampling kind of being far away from the mean. And the smaller your alpha value is, the closer to 0 it is, then the less tolerance you have. And so it means that's kind of like more important that your things aren't that different. So these alpha values really are arbitrarily chosen, but it depends on the situation. Like if you're trying to do a hypothesis test for something like airline safety, like where people's lives really are at stake, then you want a very small alpha value because you don't want to make a mistake, right? Or if it's something that's not too important, like the number of peanuts in each like little airline bag of peanuts, well, then you can have a much larger alpha value while you're doing your hypothesis testing. Right? The context of the situation is always going to determine those alpha values. And the critical values are really just a standardized value that corresponds to our alpha value, depending on the test we're doing. So those would be like t values, z values, chi-squared values, etc. And we'll just be pulling those from like tables once we know our test and our alpha value. But we still have to know what we compare the critical and the alpha value to, and that'll be our test statistic or our p-value. Okay, so the comparisons we actually end up doing is we're always going to compare alpha values to p-values, and we're always going to compare critical values to our test statistic. But if we look at the restandardization where we force mu to be at 0, then that means our test statistic could be positive or negative. And so kind of adjust for that scenario, we instead of comparing the true crit value and the true test statistic, we always compare the absolute values of those quantities instead. So I really prefer working with like the alpha and the p-values for this comparison step, but they're not really related directly to the picture we were looking up here. However, the critical value and the test statistic are. When we look at this critical value, we'll get some number out of it. And so in our example, that might be something like z star. And so that's comparable to our test statistic. Maybe z star is right about here. And so we can kind of look at that graph and then compare whether X bar is to the left or to the right of that Z star in our comparison process. And depending on how they're situated next to each other, it will draw different conclusions. All right, so when we're doing our comparison step and drawing our conclusions, there's always just one of two conclusions that we will reach, and that is we will either reject the null hypothesis in favor of the alternative hypothesis, or we will fail to reject the null hypothesis. Notice we never accept the null hypothesis in this process. So what are we really doing when we're rejecting the null hypothesis in favor of the alternative hypothesis? What we're really saying is that these different results between like our sample average and our mu in this case is not likely due to chance or probability. And in the second conclusion, when we fail to reject the null hypothesis, what we're really saying is there's not enough evidence to say that our null hypothesis is wrong. The difference could be actually just due to chance. Like the probability of that kind of different result happening is high enough to where it's not that unusual or unexpected. And that's going to tie back into that alpha value or our tolerance or threshold. All right, so then how do we draw these two conclusions? It depends on if we're comparing alpha and p or the critical values and the test stats together in the following way. So we will reject our null hypothesis if the absolute value of our test statistic is greater than the absolute value of our critical value, or we will reject the null hypothesis if our p-value is less than our alpha value. So remember, in our little picture up here, our critical value is represented by Z star, or really the absolute value of Z star, since this is to the left of 0 and negative. And so let's see, we have to remember these are kind of both negative numbers. So our critical value and absolute value is actually smaller than our test statistic and absolute value, right? This may be maybe like -4, and that's like -2. So when we take the absolute value, their positions switch. So in this kind of picture, we would reject the null hypothesis. And what's nice about looking at this test statistic versus the critical value is that we can have this visualization from that critical value Z star in this case, and that creates in our picture this little zone. We can refer to this as like the zone of rejection, right? And so if our test statistic falls in that zone of rejection, then we're going to reject our null hypothesis. This is what it looks like for a left-tailed test. On the right-tailed test, everything would just be flipped over on this side. And so our zone would be over here, and we want our test statistic to be a little bit further to the right of that. Because if it is, then our test statistic is greater than our critical value when both are taken in absolute value. So we have this nice visualization for comparing this test stat to the crit value, but I still prefer comparing the p-value to the alpha value. The p-value is like the probability of this event kind of randomly happening or happening by chance, and alpha value is like our threshold or tolerance for that chance. And another easy way to remember this comparison versus the kind of weird, potentially sometimes having to flip stuff around comparison with the test statistic and the crit value is this little phrase. And that phrase is kind of funny. It says, if P is low, then reject HO. So if P is low, reject HO. So P is referring to the p-value, and low is referring to, is the p-value less than your alpha value or your tolerance or threshold? If that is the case, then we reject our null hypothesis. And if neither of these is the case, well, then we're in the second conclusion where we fail to reject our null hypothesis. So remember, the only two outcomes here, the only two conclusions we can draw is we can either reject the null hypothesis or we can fail to reject the null hypothesis. We never accept the null hypothesis. All right, we talked about the 5 C's and some of the theory behind this hypothesis testing procedure. Now let's go ahead and look at an example where we go through this entire process of the 5 C's and complete a hypothesis test. All right, so in this example, we are told that a student thinks the average score on a stats exam is 65 or 65%. The instructor, however, thinks the average is higher. A sample of 10 students' exam scores are taken at random and are assumed to be normally distributed. We want to perform a hypothesis test on that instructor's claim using a 5% significance level, and here is our sample set of those student exam scores. So we're going to have to go through our 5 C's process, and remember, that first step in the 5 C's is creating a hypothesis. So remember, when we are creating our hypothesis, we usually start with the alternative hypothesis. That is the claim we're actually trying to test here. And so the instructor's claim is they think the average is more than 65. So in symbols, we'd write that as our alternative hypothesis, saying our average or mu is greater than 65. Well, then the null hypothesis is always just the opposite of our alternative hypothesis. So that would be mu is less than or equal to 65. But remember, we always are lazy and write that with equality instead. So we've created our hypotheses. Our alternative hypothesis, the thing we're trying to test, is that mu, the exam average, is greater than 65. And our assumption, or the null hypothesis, is that mu is 65, or really less than or equal to 65. Okay, the second step in our 5 C's is we have to check our conditions, right? We have to make sure that we have the right setup to do our hypothesis test in the first place. Otherwise, that reformatting and standardization isn't really going to work out. Well, we have to check to make sure our sample is random. That's something we always require. And I think that it was said somewhere, right? Yeah, the exams scores are taken at random. So our conditions are we have a random sample. And the other condition we needed is a normal distribution, or at least a sample size of 30 or more when we're looking at means. And in this case, we are told that we can assume we have a normal distribution. So we are good to go. All the conditions that are required have been met. So now we're ready to move on to that third C. So remember, that third C is our calculate C. So now we're ready to calculate our test statistic as well as our p-value. And so maybe I should have put this up in the condition step, but the other thing we have to know is like which kind of distribution makes sense to use here. And because the kind of standard deviation for the population is not given, we're going to use a student's t-test, use TDF, where DF, remember, is like the degrees of freedom here. Our sample size was n equals 10, and the degrees of freedom are always 1 less than that. So we'll use TDF with DF being equal to 9. All right, so we're not going to do this calculation by hand. Instead, we're going to do it using a computer or a calculator. And if you have a TI-83 or a TI-84, it's pretty quick and easy to do. Let's go ahead and show those steps on the screen over here as I type them in and explain everything. So the first thing we have to do is make sure our data is entered into a list. So we can just go to Stat and Edit, and then clear out list 1 if it has anything in there, and then enter in our 10 raw exam scores from our sample. So once we have our 10 exam scores entered into our list in our calculator, we then want to hit the statistics button, the stat, and then use the right arrow key to navigate a couple screens over to that test screen. And here we have to pick the correct test depending on our earlier work and notes that we've made. And here we earlier noted that we need to use a student's t-test or just a t-test for this hypothesis test based off the distribution and everything else. So in my calculator list, that is number 2. So we'll highlight number 2, that t-test, and then hit enter. And then it's going to bring us to a screen where it's going to ask us for some information. Our inputs can either be data or stats. In this case, we're entering some raw data in from a list. So we'll just keep that hovered over data. The next thing it asks you is for the average. This is the average being used in your null hypothesis. And so that's going to be mu naught equals 65. It then asks you what list is your data in, and that's an L1. The frequency we're just going to leave as 1. Then that next line is really asking you about your alternative hypothesis. Do you think your alternative hypothesis is not equal to mu? Do you think it's less than mu? Or do you think it is greater than mu? And in our case here, we're trying to say that it is greater than 65. So we want to highlight that third option where we have greater than mu naught. And then from there, we can either calculate or draw, depending on if we want to look at that picture with our like region of rejection, or if we just want to get those numbers to compare like our p and alpha values together. But once we have all this entered into our calculator, let's just go ahead and hover over that calculate option and then hit enter. So that's going to return a few values for us. We see that t is 1.978. That'd be like our test statistic. We see that p is 0.0396, and x bar, the average for our sample, is 67. There's a standard deviation and sample size in there as well, but the real things we focus on are like that t-value and that p-value. So we're just going to focus on this p-value of 0.0396 that we got and compare that to our alpha value, which is our significance level given in the problem statement. It was said to be 5%, but we want to convert that to a decimal of 0.05 before we compare it to our p-value. And remember, our rule is if p is low, then HO has to go. Or if p is low, then we reject HO. And here we can see that p 0.396 is less than alpha of 0.5. And so that means we reject our null hypothesis. So in this case, we reject our null hypothesis in favor of the alternative hypothesis, meaning that it is true, the instructor was right, the average is going to be more than 65. And so further interpreting this p-value before we summarize our conclusion. So if p is less than alpha, then we reject our null hypothesis, but let's remember why that rejection is taking place. So if p is equal to 0.396, then we can interpret that in the way that if our null hypothesis is assumed to be true, then there's only like a 3.96% chance of our sample population being more than 65. And that's a pretty small chance. It's smaller than our 5% threshold of acceptance. And so because that's like such an unlikely event, we must reject our null hypothesis. Our assumption must not be true. All right, so to finish this example off, we have to do our fifth C, which is write up our conclusion. And our conclusion can be written in the following way. At a 5% significant level, the sample data shows sufficient evidence that the mean test score is greater than 65.